Hi, everyone. Welcome back to Dave's Math Channel. I'm your host, David Tear, and this is my sixth video in a series on complex numbers. Today, I'm going to talk about a very important result from complex analysis called the fundamental theorem of algebra. And let's begin. So, what does the fundamental theorem of algebra say, and why is it so important? Well, what it really says is if you have any polynomial, a polynomial is just a special type of function. It's a function that consists of powers of its variable, a finite number of powers of x in this case. It's a univariate polynomial, so just one variable, x, or usually called z when you're dealing with complex numbers. So it's just, it has the form Cn z to the n plus Cn minus 1 z to the n minus 1, so on, up to C1 z plus C0, and that all equals 0. So it becomes an equation when you set it equal to 0. That's what's called a polynomial equation. So, a lot of the equations we study in math are polynomial equations. Good examples, a quadratic equation, that's just a polynomial of degree 2. I guess linear is the simplest, like x minus 5 equals 0, or 3x minus 8 equals 0. These are usually the first kind of equations you learn when you first learn algebra. Linear equations, their graphs are just a straight line. Those are pretty trivial to solve. And if the roots are real, then I mean, if you have the coefficients, these numbers k going from 0 to n are called the coefficients. And if, for a linear polynomial, there's only two possible coefficients, c0 and c1. If they're both real, then the root's going to be real, obviously. And, if they're complex, the root will be complex, but there'll still be a root, and it's pretty trivial to solve. But I guess the next most interesting case is quadratic. I'll get into this more, but let's just consider the general case for now. So imagine we have a polynomial equation that looks like this. Cn x to the n plus Cn minus 1x z, I guess you could call it z. So Zn z to the n plus Cn minus 1 z to the n minus 1 plus dot dot dot. Well, C1z plus C0 equals 0. Well, what the fundamental theorem of algebra says is that this polynomial, it's a polynomial of degree n. So every polynomial of degree n has exactly n roots. And some of these roots might be repeated. But basically what it's saying is that you can factor this polynomial completely over the complex numbers. And they do it at the bottom. So you can write it in the form f of x or f of z equals, and then you always take the leading coefficient, which is Cn. So you factor that out. And then you just have this product, x z minus r1, z minus r2, up to z minus Rn, where R1, R2, dot, 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 up to Rn are the complex roots of this polynomial. What this formula is basically saying is that all the roots, there's exactly n roots, counting multiplicities. You might have a factor squared or cubed, and then that just means it has multiple roots. But it always has exactly n roots, counting multiplicities. So in other words, it factors completely over the reals. It factors completely into linear factors. And that's a really nice result because that's not true over the real numbers. For instance, the polynomial x squared plus 1 does not have any real roots. Its roots are plus or minus I. So its roots are complex, they're imaginary. But even if you had imaginary coefficients, these c's don't have to be real. They could be imaginary. They could be complex, arbitrary complex numbers. Even if that was the case, you would never. All your roots are still going to be complex. So, and another way of saying this is that the field of complex numbers is algebraically closed, and the field of real numbers is not algebraically closed, nor is the field of rational numbers. So this, complex numbers have this nice property that they're algebraically closed, which is basically what the fundamental theorem of algebra says. So this is a very important result. And I'm not going to prove it because the proof is very complicated. The proof actually involves some very advanced calculus. It involves complex analysis, which is basically calculus applied to complex numbers. That's like a second or third year college level course. So I'm not going to get into that. But what I'll do is I'll give you some examples. So now we're going to get a little bit more down to earth. So now let's just consider, I guess, the first interesting case. The linear case is obvious, but the quadratic case is the next most interesting. So I think you guys all learned the quadratic formula in high school. You have a polynomial ax squared plus bx plus c. That's called a quadratic polynomial. You set it equal to 0, and of course your leading term has to be non-zero. I should have said that earlier. When you write down this polynomial CN, we're always assuming the leading term in this nth degree polynomial is non-zero. That's what makes it an nth degree polynomial. So we're assuming here that A is non-zero. And if that's the case, then this formula, which I'm sure you guys all learned, x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. That is the formula for the roots, and there's always two roots counting multiplicity. You might have learned in high school that there's not always two roots, because if you're only worried about real roots, that's not always the case. And this quantity inside the square root is what's called the discriminant. B squared minus 4ac is a very useful quantity. It's known as a discriminant. Sometimes people write it as D. So if D is positive, then I think you guys all learned that there's two real roots. And then if it's 0, there's exactly one real root. You can, I mean, one way you can see this geometrical, I don't know if I showed a picture here, but what a lot of people do is no, I didn't do it, but what a lot of people do is they show a picture of parabola. So this quadratic equation, the graph of that quadratic equation is a parabola. On the XY plane. We're not necessarily dealing with complex numbers yet. As a matter of fact, we're not. If we just think of x as a real variable. So you get two roots if the parabola intersects the x-axis, and then the roots are just the the y-intercepts of it's where it intercepts the x-axis. The values of x, so where it intersects the x-axis, and so there's going to be two distinct roots if the discriminant is positive. There's going to be one root if the discriminant's 0, because then this thing is really a perfect square. So that's really a double root, because then this is going to factors a of x minus r quantity squared. And then if it's less than 0, you probably learn that there's no solution or no real root. And it's true there's no real root, because in this case, the parabola does not intersect the x-axis. But there still are two complex roots in that case, two imaginary roots. So even though it doesn't intersect the x-axis, that just means there's no real roots, but there's still two imaginary roots. So anyway, and like I said, the key thing here is the discriminant. Discriminant tells you whether the roots are real or imaginary. If the discriminant is negative, then the roots are imaginary. It has two imaginary roots. If the discriminant is positive, it has two real roots, and if the discriminant is 0, it has one repeated real root. So, but it always has two roots counting multiplicity. So that's a special case. Yeah. Oh, yeah. I did include the graph of the parabola. So here's an example. Say y is x squared plus 4x plus 5. Okay, as you can see from this graph, this quadratic equation has no real roots because it doesn't intersect the x-axis. But you can still solve for the roots using the quadratic formula. You just get a thing with a negative, the discriminant's minus 4 in this case. So the answer is going to be minus 4 plus or minus square root of minus 4. But we know that the square root of minus 4 is, we can write that as just I. We can factor out an I to get rid of the minus sign inside the square root. So it's going to be I times the square root of 4, or 2I. So your two roots are going to be negative 4 plus or minus 2I over 2, or minus 2 plus or minus I. And notice something else interesting here. These roots are complex conjugates of each other. And that's not a coincidence. It turns out that if you have any polynomial, it doesn't matter what the degree is, if you start with any polynomial with all real coefficients, and that's key, the coefficients have to be real. But if you start with a polynomial with all real coefficients, it turns out that every imaginary root is paired with its complex conjugate. So you get complex conjugate pairs of imaginary roots. And another interesting consequence of that is if your degree of your polynomial is odd, that means you have to have at least one real root. Since the imaginary roots are all paired, that means there have to be an even number of them. So, for instance, if we went to degree 3, that means you could either have 3 real roots or maybe one, uh, well, I'll get into that next. Here's the case for cubics. So if we have a cubic polynomial with real coefficients, its graph can look like one of these three things. There's no other possibility. Um, so the first case shows 3 real roots that could intersect the x-axis in 3 different places, and then you get 3 real roots. Or one of the roots could be repeated, which is the second case, and then you have 2 real roots, one of them repeated, so you still have 3 real roots counting multiplicity. But in the third case, the one on the right, you only have 1 real root, but then you still have 2 imaginary roots. And those imaginary roots, just like in the quadratic case, are complex conjugates of each other. So those are the 3 things that can happen with a cubic polynomial. And I'll give you an example. This is what I'm going to finish up with today, I think. But so here's an example of how you would factor a cubic polynomial. And you probably learned, so here's an example. P of x is x cubed minus 2x squared minus 8x minus 35. I think you guys learned that if you're trying to factor a polynomial of degree 3 or larger, the first thing you probably want to do is what's called synthetic division to see if it has any rational roots. In this case, it does. So it turns out that 5 is a rational root of p of x. And you can check that yourself by doing synthetic division. And when you do the synthetic division, you'll find that you find that when you divide by x minus 5, you're left with this quadratic polynomial x squared plus 3x plus 7. And whenever you have a quadratic polynomial, you can always use the quadratic formula to solve for its roots. So I did that here on the right, and it turns out the two roots of the quadratic polynomial are minus 3 plus or minus I times the square root of 19 over 2. So they are imaginary in this case, and they're complex conjugates of each other. So now to completely factor the cubic polynomial, we write p of x as x minus 5 times q of x. We've already factored q of x. It's just x minus each of these roots, so we have to make this a plus 3. We negate the roots. So it's going to be x plus 3 minus I root 19 over 2, and x plus 3 plus I root 19 over 2. Those are the two roots of the quadratic polynomial, and then you also have x minus 5. So that is the complete factorization over the complex numbers of this polynomial that we started with. Pretty neat. And I'm just going to give you one more example, actually. Like I said, the coefficients of your polynomial do not have to be real. And in this case, they're not. But this is actually a pretty easy one to factor. So if you just kind of do this by inspection, I think you can see that I is a root. Because you have this pattern here, z cubed minus I, z squared. We can write that as z squared times z minus I. And then you look at the last two terms, 4z minus 4I. Well, that's just 4 times z minus I. So it's pretty easy to see that z minus I factors. And then if you factor z minus I out, you're going to be left with z squared plus 4. And that's easy to factor. That's just z plus 2i times z minus 2i. So your complete factorization is going to be z minus I times z plus 2i times z minus 2i. And note that this z minus I factor is not paired with its complex conjugate. Even though I is a root, minus I is not a root, and the reason it's not is because polynomial started with doesn't have all real coefficients. So anyway, those are just some examples, and you can do higher degree if you want, but the higher the degree gets, the harder it gets to factor them. I figured I'd stop with cubic polynomials. Anyway, that's my video on fundamental theorem of algebra, which, like I said, is a very important result in complex analysis. So thank you for watching. Long live math, and I'll see you next time.